Hey everybody, wow, it's been a long review here, so let's zoom out here a little bit. This is part 3 of the stoichiometry test review. And let me get this zoomed in here a little bit. I cannot emphasize enough, make yourself a simple MVP triangle, use a pencil, if that'll help you map out so you know how many conversions you need to do. So we are working on the back now. So, question number 25. Let me zoom in so we get that nice and big for those of you watching on the little tiny screens. How many moles of carbon, hydrogen, and oxygen are in 1 mole of glucose sugar? So, C6H12O6, the fuel for our body. If we have 1 mole of this, now here's what I want you to imagine. Imagine we've got 1 mole of this. We've got Avogadro's number of those sugar molecules. If we could somehow zap this with, I don't know, gamma rays and blow it apart, it would blow apart, or it would change into, we'd get 6 carbons, right? Because there's 6 carbons there. Plus, we'd get 12 hydrogen atoms, assuming they weren't, right away recombining into a gas. Plus, those 6 oxygens would end up being plus 6 oxygens. So now, if you take a look at this now, we've just, by blowing this apart, we've just turned this into kind of like a balanced equation. 1 mole of glucose sugar, if you could separate it into its parts, you'd end up with 6 moles of carbon, 6 moles of hydrogen, 12 moles of hydrogen, and 6 moles of oxygen. So there's going to be 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen if you took 1 molecule of this and 1 mole, of glucose and blew it apart, because when you blow it apart, it's kind of like the sum of the individual pieces is more than the sum here. We get a whole bunch more different particles. Okay, so let's take a look. Bang! Dynamite! Woo! Okay, it's been a long day here. So, okay, there we go. We got a stick of dynamite right here, and this is kind of burning right there. Okay, that's going to be explosive. We know that. So, we want to know how much carbon, hydrogen, nitrogen, oxygen are in 1 mole of dynamite. Well, 1 mole of C7H5N3O6. So, if we could pull it all apart, okay, explode it completely, and so it's just goes to all of the elements, not just into the compounds that it make. So, there are 7 carbons. Then we would get 5 hydrogens blown apart. We would end up with 3 nitrogens floating around and 6 oxygens. Now, if that was just one molecule, we just end up with this many atoms of each of those. But this is 1 mole. This is Avogadro's number of those. Oh, pardon me, hail sneezer. So what's going to happen is, since this is 1 mole, we're going to end up with 7 moles of carbon, 5 moles of hydrogen, 3 moles of nitrogen, and 6 moles of oxygen will be in that 1 mole of dynamite if we break it apart. So there you go. What does conservation, keeping or saving, is what that root word, keeping, saving. And when you're taking the test, you can write on your tests, okay? Do little notes like this. What does conservation of matter mean? That's the one you can't create or destroy. Can't destroy. Okay, I started there. Destroy or create atoms. Matter. You can't create or destroy matter. And in chemistry, what that happens is that we have to balance equations. If we got water splitting into hydrogen and oxygen as it does, hey, we don't have enough oxygens there. We only have 1 oxygen and 2. We need to double the amount of oxygens, which means we double that. So when we balance chemical equations by balancing the number of atoms, that ends up that we have the same mass over here, because these mass of atoms will always have to equal the mass here. We're not creating or destroying any matter. We're just rearranging it. And that's what the law of conservation of matter is about. And when we balance equations, we're balancing the atoms. We use coefficients to do the balancing, but it ends up we're counting the atoms to make sure there's the right amount. Now the last concepts we went over. Question number 28. Now there is a slight mistake. Sorry about this. It says empirical and molecular formulas. You don't need to do molecular formulas. That's a AP chemistry and an honors chemistry question. We're just doing empirical formulas. Now, the first step on these is that since we know we have this percent of carbon and this percent of hydrogen, we're going to assume that we have 100 grams of the compound that this came from. So if we had 100 grams of the compound that this came from, if 85.7% of it is carbon, then we know that we have 85.7 grams of carbon, which would mean, okay, then we know that there are 14.3 grams of hydrogen in that as well. Now the next step is, so we assume there's 100 grams and we convert them into grams. Now we got to convert these to moles. So now we need to divide by the molar mass, because when we convert this to moles, you always need to have what you were given on the bottom of the fraction and moles up here. And let's see, 1 mole of carbon, and we look on the periodic table, is 12 grams. You're probably getting that. So we can cancel those two out. Uh-oh, I did not have that one pre-done for you. Let's see, we have 85.7 divided by 12. We end up with 7.14 moles of carbon. Now, and I'd like you to go to 2 decimal places on these. Now let's do the same for hydrogen. Well, actually hydrogen's easy, because hydrogen, there's 1 gram of hydrogen in 1 mole of hydrogen. So that's pretty easy. We end up with 14.3 moles of hydrogen. So the next step is, after we convert these into a mole, so you convert mole. Now the next thing is we need to divide by lowest mole. So the lowest mole number is 7.14, and divide by 7.14. Well, we can tell that's going to be 1, and this is going to be 14 is going to be just about 2. So carbon 1, hydrogen 2, or if you said H2C, that's even better. That'll be fine. Now, for all of the next ones down here, we do it exactly. So I'm not going to go through every single one. I'll help you get it set up, but you're going to have to do the math, because I'm not going to go through and do that all for you. So when we read now, there are some, now here, look at here. We've got 380 grams of a compound with nitrogen, and 140 grams is nitrogen, and 240 grams is oxygen. So what we have to do is, we have to convert that into a percent, and then it's just like we did this one. So for nitrogen, there is 140 grams of nitrogen in 380 grams of this, whatever this compound is. So we come over and we do the math, and we're going to end up with 0.37, and that turns out to be 37% nitrogen, because we just convert the decimal into the, so we got 37% nitrogen, and it's only 2 compounds. So I'm not even going to bother to do the math, because these 2 compounds, carbon and they have to add up to 100. So I'm going to get on my calculator here. Let's see, 100%. I'm going to subtract. We know that there's 37% nitrogen, so 63% oxygen is what we'd have. Now, if you did the math, you could have gone through and done 240 grams divided by 380, but it's going to come out to 63%. Now, at this point, now you say, for nitrogen, we have 37 grams of nitrogen. For oxygen, we have 63 grams of oxygen. And then you're going to do the same things we did in this one here. You're going to first convert these to moles by dividing by the molar mass. Then when you get the number of moles over here, you'll get a mole. You're going to take a look and you're going to divide these. Now, here's what's going to end up happening. You're going to end up with this number. Okay, I'm just going to tell you, when we do all the math, you should end up with about 2.64 moles of nitrogen, and you should end up with about 3.9 moles of oxygen. When you divide these, you got to divide by 2.64, so So we got to divide by 2.64, divide by 2.64. What we end up, we get a ratio that we get 1, and it's going to be to about 1.5. So now the problem with this is, let me write here, nitrogen and oxygen. So we got 1 to 1. It's okay to have 1 nitrogen. We cannot have 1.5 oxygens. That is not allowable. So what you have to do is, if you end up with a 0.5 here, we need to multiply this by 2. So that'll distribute that. That'll become N2 and O3 is what the empirical formula would be for that one. Okay. For part C, we've got, now they're giving you more. Okay, we don't need the molecular formula. Sorry, we don't need to go that far. Titanium and sulfur. Titanium is 43%, which means we got 43 grams of titanium. Sulfur, well, we need to do 100% minus 43%. And that's going to be 57 so we got 57% sulfur, which is going to become 57 grams of sulfur. And then you can go through and you can work out the calculations from there. Same step, turn it to moles. Then you're going to, once you get the moles, you're going to divide by the lowest number of moles. And then those numbers will end up being the subscripts we put in here. And if it ends up being a 0.5, you multiply by 2. For part D, find the empirical formula for 50. Okay. So let's see here. So we've got to find a formula compound of hydrogen and carbon. Okay, we're looking for hydrogen and carbon. Oh, now they're giving you extra. Look at, they've told us we've got 17.2% hydrogen. Well, there's just 2 compounds, so those 2 add up to 100. So let's do 100% minus, what was it, 17.2? 17.2. So now there's going to be 82.8% carbon, and then that becomes 17.2 grams of carbon, 82.8 grams of, 17.2% of hydrogen, 82.8 grams of carbon. Convert it to moles. Whatever is the lowest number of moles, it's probably going to be this one, I have a feeling, but yeah, because this will be 17 moles it'll turn out. So you're going to divide that by the lowest number, and then if they're whole numbers, the ratios, that'll tell you how much carbon to hydrogen you have. Percent compositions, those I think are almost easiest. When you do percent compositions, you got to first use your periodic table. SN is 10, it's 119 grams per mole. And then chlorine is 35, but there's times 2. So that ends up being 35 times 2 is 70 grams per mole. When you add that up, you get 189 grams per mole is how heavy SnCl2 is. Now for the percent composition, 10 is 119 grams SN divided by 189 grams per mole in the whole compound. And when you do that, let's see, 119 on my calculator divided by 189 comes out to be 0.6, I'm going to say 0.63 because so it was 0.629, 0.63, which will be 63% tin. And then we're going to come over here. Now, let's be careful on this one now. In this compound, okay, so we know the compound is 189 grams. Now we got to do the chlorine. But now we've got 2 chlorines. So we don't want to just say, hey, chlorine is 35 divided by 189. No, we've got 2 chlorines. So let's say those 2 chlorines are going to be 70 grams per mole for chlorine. I'll just say Cl2 just so we know that. And then we got 189 grams per mole. And actually, it should turn out, let's see here. Let's see if the numbers, hopefully I don't hang myself with my students. 70 divided by 189 comes out to be, wow, look at that, 0.37, which turns out to be 37%, and that's going to add up to 100%. You are done with that problem now because you just got to get the percents. You can do the same thing here. just remember that when you go to, let's say, do the carbons, you got to find out the total weight of this one and the molar mass. And when you get the molar mass of the whole compound, molar mass, that's going to be the 3 carbons and 8s. Remember, you've got to do 12 times 3 up here. You need this to be 36 up there, because that's how heavy the 3 carbons weigh in that. And then when you do the hydrogens, just remember, you've got to do all 8 hydrogens, so that'll be 8 grams of hydrogen divided by whatever the molar mass is for that whole compound. It's going to be like, I don't know, what is it? It's 44 or something. Down here, okay, that's a big one. Okay, we practiced that in our starters the other day. So, I mean, the 2 aluminums end up being 54 grams. Now, there are 2 times 3 chromiums. So when you figure out the chromiums, chromium on your periodic table weighs 52, but you've got to multiply that by 6. And you should end up that should come out to, well, you can do that. Then the oxygens. So the oxygens, we've got 7 times 3. So we've got 21 times 16. Oxygen weighs 16 on the periodic table. You can get that. So that'll be, when you add those all up together, this plus that, you'll have your molar mass. You'll put that weight under here. And then for aluminum, you're going to do 54 divided by the molar mass. You'll get a percent. Then for chromium, you're going to do 52 times 6 divided by the whole molar mass. You'll get that percentage. And then you'll do oxygen. You'll do your 21 times 16 divided by the whole molar mass, and you'll be done. So I don't have the actual numbers. You can check in class tomorrow, but that's how you go through the process. Good night and goodbye.